Hi there. During this session, I will be talking about a wave phenomena known as standing waves or stationary waves. As you can see from the example, this is a situation where the wave apparently doesn't move. Okay, so it appears stationary to the observer, and we're going to talk about this in more detail. So let's first think about how these standing waves are formed. So standing waves are formed by two waves of same speed, wavelength, and equal or almost equal amplitudes traveling at each other from opposite directions. And what happens is when they travel from each other opposite directions, they constructively interfere, and that constructive interference produces a standing wave. So standing waves and travelling waves are different from each other because a standing wave has to be created from the superposition of two waves travelling in opposite directions. Now, don't forget that these two waves travelling opposite directions could just be caused by a reflection of a wave of a certain point causing this to happen. And the big difference here is between a standing wave and a travelling wave is that a standing wave, no energy or momentum is transferred down the string. Okay, so no energy is in motion. So let's think about the parts of a standing wave. We have what's known as nodes and antinodes. Now, the bits which actually move backwards and forwards, and there are parts of a standing wave which are moving all the time. These are known as the antinodes. So these are the locations which go from maximum to maximum on the size of the amplitude and the direction and amplitude of the wave. We also have parts of the standing wave which do not move at all. Now these are known as nodes, and these are fixed points. For instance, on a string, we have to have a node at one end and the other end, because that's the end of the string. There's a practical consideration to take place there. So nodes are the parts of the standing waves which do not move. Now, if we think about standing waves, first example we're going to talk about is the standing waves which form on a fixed string. So like the kind of thing you'd find on a guitar. And what happens, and there's a kind of a musical terminology here, we have what's known as the first standing wave is known as the first harmonic, or sometimes the fundamental. And then the next most standing wave which can form is the second harmonic, or the first overtone. And then we come to the second overtone, or the third harmonic, or the third overtone and the fourth harmonic. Now, these waves are specific because they have to have, for a fixed string, they have to have a node at either end of the string. So there's a requirement of this situation. If we look closely at the patterns here, we can see that on the first harmonic, the actual wavelength of the wave is going to be twice that of the length of string in the first place. If we look at the second harmonic, what we find is the wavelength is going to be equal to the length of the string. This pattern is repeated, and what we find is the wavelength of a certain harmonic, so harmonic n, is equal to twice the length of the string divided by the number of harmonics. Now, if we remember about the relationship between wavelength, frequency and speed, we can also ascertain that the frequency of the specific harmonic is equal to the harmonic number multiplied by the speed of the wave divided by 2 times the length. So there's a pattern there which is useful to be able to solve problems and understand the different situations. Now, if we think about a guitar string, what you crucially normally hear is the first harmonic, and then the subtleties in the sound come from the second and the third and the fourth harmonic existing from when you pluck the string. So that's the patterns on a fixed string. let's think about this as a question now. Which standing wave has the highest frequency? So I've got two standing waves here. Now think about the answer. Hopefully you recognize the standing wave with the highest frequency is going to be wave number 1 here. And that's because it has the most nodes. So the more nodes there are, the higher the frequency. So that's fixed strings. Let's talk about something else now. Let's talk about columns of air. I've got my test tube rack here. I can make noises with the test tubes because of the columns of air which are created by blowing into them. What I should find is that the length of the air column does have an effect on the natural frequency of the column of air. And what should occur is that the shorter the air column, the higher the natural frequency of this situation. Now, so the higher the natural frequency of the situation, and that's what we're going to be able to hear. So we're going to talk about two situations with harmonics of pipes. So this is the harmonic of the air. So we're talking about the waves or the standing waves which we set up in either a closed pipe or an open pipe. Now in a closed pipe we can see that the entrance to the closed pipe must have an antinode in. The reason for that is because that's where the energy is given to the system. And at the same time, there must be a node found at the end of the closed pipe to allow the standing wave to create from waves going in and reflecting from the end and coming back again. Now, this crucial feature means that the first harmonic, the fundamental harmonic of a closed pipe, is going to have the length of the closed pipe is going to be 1/4 of that of the first wavelength, of the wavelength of the first harmonic. With an open pipe, again, open pipes are going to require that there's going to be an antinode at the entranceway to the pipe. That's where the energy is going into the system. So here, for an open pipe, we find that the wavelength, or the length of the string, is going to be equal to half the wavelength of the first harmonic. Just with the fixed string, we can then consider the second harmonic. Now, the second harmonic for an open pipe here is again the next situation where we can have two antinodes at the end of the pipe. So in this case, the second harmonic will have two nodes. There's an antinode at either end of the pipe, and what we see here is the wavelength of the second harmonic is equal to the length of the pipe. Now, note here that the way harmonics work is as they go from the first to the second harmonic, then what you're normally doing is you're doubling the frequency. Now, with a closed pipe, as we need to have if we double the frequency, there's going to be a node at the entrance to the pipe, and this can't happen. The closed pipe must have an antinode at the entrance to the pipe because that's the way that the energy of the wave goes into the system. So for that reason, there's no second harmonic in a closed pipe. We can carry on our pattern though to the third harmonic. The third harmonic for a closed pipe. Here we see a situation where we have an antinode at the entrance to the closed pipe, and the length of the pipe is equal to 3/4 of the wavelength of the third harmonic. The open pipe length is equal to 3 divided by 2 wavelengths of the third harmonic, and that pattern continues and continues. So let's just recap on the general formula. For a fixed string closed at both ends, we recognize that the harmonic multiplied by the wavelength equals twice the length. And this can be rearranged to work out what the wavelength is or what the length of the string is. Moving this forward, that means the frequency is going to be equal to the harmonic multiplied by the speed of the wave divided by twice the length. One end closed pipe. Here what we find is that the harmonic times the wavelength equals 4 times the length. where n is an odd integer. So it has to be an odd integer. So it's going to be 1, 3, 7, and so forth. The frequency of these harmonics is going to be the harmonic multiplied by the wavelength divided by 4 times the length. The third and final example, an open both-end pipe, we find is actually ends up having very similar pattern to that of a fixed string. So the harmonic multiplied by the wavelength equals 2 times the length. So therefore the frequency equals the harmonic times the speed of the sound divided by 2 times the length. I'll quickly end with showing an example of a question you might come across. A standing wave example. So the speed of a wave on a string is given by the formula the velocity equals the square root of the tension divided by the mass per unit length. Deduce the frequency of the fundamental in a string of length L, so therefore this is still a general term question, and then use the answer to A to estimate the tension of the string of a violin. Okay, frequency of 440 Hertz. Pause for a moment, I'll let you do these questions. The wavelength for the fundamental is 2L, so using the fact that frequency is equal to the speed divided by the wavelength, I get a formula for working out the frequency, and then from here I can work out if I approximate length to be 0.5 meters and the mass per unit length of a typical violin is 2.0 times 10 to the minus 3. It tells me that the tension in the string of a violin is going to be about 400 newtons. And with that, I hope you understand fully how a standing wave works.